Welcome back to another lesson on logarithms. The objective of this lesson is to find a number x such that e to the x equals 10. That number x we call the natural logarithm of 10. Remember that logarithms are simply the inverse function of an exponential function. You may be wondering why I have devoted an entire lesson to one number. We will see in upcoming lessons why this particular number is so useful. So here I am just laying the groundwork. We saw in the last lesson how to change the base of any logarithm. That is repeated here for base b equal to 10. Since we want to know base 10 logarithms, we will have to divide by the natural log of 10, as seen in the last line. Note that sometimes the base 10 logarithm of a number is referred to as a common logarithm. Common logs are used often because most people use a base 10 number system nowadays. That is our familiar decimal notation. Of course, we use the natural log, base e, because we know this series expansion, which was derived from the geometric series. The natural log is the inverse of e to the x, where e is approximately 2.718. So for z equals 10, we get x equals 0.818. This is less than 1, so the series will converge. However, experience tells us this will converge rather slowly. Let's make x smaller to speed up convergence. Try taking the eighth root of 10. That can be done using a built-in calculator function or employing Newton's method. In the last lesson, I explained why the eighth root is useful, and I'll summarize again at the end of this lesson. Notice that plugging that in spits out x equals 0.14. This is much smaller and will converge more quickly. This is a spreadsheet showing term-by-term calculations for the series expansion of the natural logarithm. The last column is twice the sum of all the terms up to that row. Notice the signs of convergence as underlined in purple and red. We have discussed this extensively in past lessons, and here it shows up again. Using laws of logarithms, we can rewrite the eighth root of 10. Multiply the answer in red from the series expansion on the last page by 8 to get the natural log of 10. That is underlined in blue. Compare that to the number from a built-in calculator function. It looks like we are accurate to 15 digits total. Not bad. This is the law of logarithms we used, by the way. Feel free to revisit that lesson if you care for more details on these. Now we are going to use this law of logarithms to compute the exact same number. In previous lessons, we have already found the natural log of 20 and the natural log of 2. I've repeated those results here for convenient reference. No need to reinvent the wheel. Let's now use them to find the natural log of 10. 20 divided by 2 equals 10, so I just need to subtract the natural log of 2 from the natural log of 20 in order to find the natural log of 10. That calculation is shown here. Notice I am limited to 14 digits past the decimal by the rules of significant figures. It is reassuring to note that this answer is exactly the same as the one we just obtained from the series. Two independent paths to reach the same destination. Back to our change of base now. To find the base 10 logarithm, we can divide the natural log of a number by the natural log of 10, which we just computed. Sometimes multiplication is easier than division, so I've rewritten the expression as some constant a times the natural log of x. A is 1 over the natural log of 10, so a equals 0.434 approximately. This is a very useful number, and we will use it in upcoming lessons. So don't forget where it comes from. As promised, I now summarize why taking the eighth root is useful. Notice the powers of 2 result in nested square roots. For example, 2 to the third power is 8, and the eighth root of a number, n, is 3 nested square roots. That is seen in the third line. This pattern continues indefinitely. Square roots are common even on some non-scientific calculators. That's the button boxed in red. If your calculator has the button boxed in blue, you can easily take any root of a number, but that's not always an option. So in conclusion, we have found that the natural log of 10 equals 2.3 approximately. What does this mean? It means that e to the 2.3 equals 10. Logarithms are the inverse function of exponentials. In the next lesson, we will see why the natural log of 10 is such a useful number, so stick around for that. If you have any questions or comments, feel free to utilize the comment section below. Thanks for watching. I look forward to seeing you again.